I've been fascinated with quantum physics for a very long time, so much so I did a PhD in it, and I wanted to share the subject with you, so I made this map of quantum physics to lay out the ideas within the subject, to set some bounds on it so you know it's not endless, and to introduce you to lots of concepts. If you're interested in them, you can dig deeper. When you're approaching a subject like this that's so complicated, it can be quite challenging because you don't know where to start and you don't know how all the concepts relate to each other. So hopefully this will put everything in context. Okay, first let's just look at the geography of this map. To the northwest we have the foundations of quantum physics, and then traveling further south we go through quantum phenomena to quantum technology. And in the south and east, we have the academic disciplines of quantum physics. In the center, quantum theory, and in the north and east, the theoretical future of quantum physics beyond what we already know. That is your quantum forecast for this video. I've also made a poster of this available, so if that's of interest, check it out in the description below. And without further ado, let's get into it. The theory of quantum mechanics developed from a set of mysteries in the late 1800s and early 1900s where reality didn't quite match the models of physics at the time. We now call these older theories of physics classical physics. There were several clues that pointed to some deeper model of reality. When light shines through a gas, the gas absorbs and emits specific frequencies of light, which we call atomic spectra. This was a mystery. There was no known classical explanation for this. And there was a lot of confusion about how atoms could be stable. In classical physics, the electrons should continually radiate their energy and collapse into the nucleus. The source of radioactivity was unknown. When you look at a hot body like the sun, it emits electromagnetic radiation in many different frequencies, and this distribution of light is called blackbody radiation. Now, the distribution we observe from black bodies didn't match the predictions from classical physics. And when you shine light on certain metals, you can make electrons fly off. This is called the photoelectric effect. This experiment showed that light didn't behave like a wave, but like a stream of particles, and was the first indication of particle-wave duality. Let's look at the foundations of quantum mechanics. A cornerstone experiment in quantum mechanics is the double slit experiment, where electrons are fired through two thin slits and make an interference pattern on a detector behind. This interference pattern is something you only see with waves, and this is more experimental evidence for particle-wave duality. In actual fact, in the mathematics of quantum mechanics, all particles are described as waves by a thing called a wave function. And the way this wave evolves over time is described by the famous Schrödinger equation. But we can never see these quantum waves directly, as all we ever detect are particles. But from the wave function we can predict where the particles are likely to turn up, but we have to do a bit of maths on them first called the Born rule, which derives a probability distribution of where the particle might be from the wave function. So quantum mechanics tells us that the universe is fundamentally probabilistic. We don't know exactly where the particle will turn up. The best we have is a probability of where it will be. This brings us to the Heisenberg uncertainty principle, which says that quantum objects don't have definite values for certain pairs of properties, for example position and momentum. You can get a flavour of this from these pictures. The first is a snapshot where the particle has a definite position, but we have no information about its momentum, which means the direction it was going and how fast it was travelling in that direction. The second picture has a motion blur, which tells us about its momentum, but now we've got an uncertainty about where the particle was when we took the picture. Another important equation is the Dirac equation, which extends the Schrödinger equation to include special relativity and describe particles with high kinetic energy. And another important foundational concept is Bell's theorem, which proved that the uncertainty in quantum mechanics is not caused by our lack of knowledge about hidden variables, but is a fundamental part of the universe. This also led to the concept of non-locality, which we'll meet a little later. Finally, we get to energy quantization, which is where objects, like electrons, can only have certain definite energies when they're in atoms. This is where the quantum in quantum mechanics comes from. And this quantization is because their wave functions can only vibrate in certain specific ways. You can see this if I reduce the atom to one dimension. The energy field of the proton in the atom is represented by this bucket shape. You can think of the electron being attracted to the proton, and so it wants to fall into the bottom of the bucket. But because the electron is a wave, it can only exist in certain modes, shown here, which are just like the vibrational modes of a guitar string, with the higher frequency modes having a higher energy. This also means that quantum objects always have a minimum amount of energy known as the 0-point energy. And this applies not only to electrons in atoms, but to everything, even to empty space itself. Now, I understand that this is all quite a lot to take in if you're new to this, but don't worry if all these terms are confusing. The point of this video is to expose you to a lot of the concepts in quantum physics just so that you know that they exist. I can't delve into every one, otherwise we'd be here forever, but if you want to dig deeper into any of these concepts, I've made a playlist of other videos that covers a lot of them. There are, however, a lot of gaps and I'm planning on filling them in the future, so if you want to make sure you don't miss out, consider subscribing to this channel for more details in the future. Okay, let's carry on and take a look at the interesting properties we see in quantum systems with quantum phenomena. Particles in quantum mechanics have many properties. I've already mentioned position and momentum, but there are many others which I've listed here. Spin is a very important property, and all particles are split into one of two categories. Bosons, which have got an integer spin and can all have the same quantum state, and fermions, which have half integer spin and can't have the same quantum state as each other, which is called the Pauli exclusion principle. Superposition is a property when a particle has a probability of being in many different states, for example, two different places at the same time. This simply means that its wave function has values in two different places, although when you measure it, it will turn up in just one place. Being in multiple places at once is confusing if we think of particles, but it's completely natural when we think of waves. For example, any point on the surface of the ocean is a superposition of thousands of different waves all added together. You may have heard of Schrödinger's cat, which is a popular description of superposition, although it's not very helpful because it was originally designed to show how absurd quantum mechanics seems, as cats can't be alive and dead at the same time. Which is true, but it's not because superposition isn't real. We now know that large things like cats lose their quantum behavior because of decoherence. Decoherence happens when a quantum object interacts with an environment and its quantum behavior is lost to that environment. Decoherence is what takes us from the quantum realm to the world that we inhabit, and you break the coherence of quantum objects when you make a measurement. Entanglement is where the wave function of two or more particles interact and mix, causing them to become a single quantum object. This means that the properties of the different particles will be correlated even if they're separated by a large distance. This concept, where the wave function that describes a particle is spread far away from the particle, is known as non-locality, and is another thing that doesn't happen in the world that we experience. There are several other very interesting phenomena which only happen in quantum systems, which include quantum tunneling, the ability for particles to cross narrow barriers because their wave function penetrates through; superconductivity, the ability for electrons to move with zero resistance at low temperatures; and superfluidity, allowing fluids to flow with zero viscosity. There's also the quantum Hall effect, which is the quantization of conductance in 2D materials, and the Casimir effect, which is an attractive force at very short distances caused by cutting out large quantum waves between two plates. And an important concept when looking at the quantum behavior of large systems are phase transitions from one collective behavior to another. These are analogous to the transitions between different phases of matter, solid, liquid, and gas. But in quantum phase transitions, it's not only temperature and pressure that plays an important role, it can also be things like applied magnetic field. Whenever we discover new interesting behaviors in physics, one of the first questions is, can we use this to develop some new interesting technology? And there's a lot of technology that we use every day which takes advantage of the amazing properties of quantum systems. Lasers use a process called stimulated emission to create beams of light with many photons which all have the same frequency and phase. Atomic clocks keep incredibly accurate time by using the frequency of light from a very specific hyperfine transition in cesium atoms and are the basis of our global positioning system. The band theory of solids describes the energy levels of electrons in many different solid materials, and it's the basis of the semiconductor industry, which has yielded many different technologies like solid-state transistors, so basically the building block of every computer in the world, LEDs, which you're probably using to watch this on, CCDs, used in every digital camera, and solar panels, turning the energy of sunlight into electricity. Electron microscopes, scanning tunneling microscopes, and atomic force microscopes allow us to see objects we can't see with optical microscopes because they can see smaller than the wavelength of visible light to resolve objects like viruses or atoms. And magnetic resonance imaging techniques are used in biology and chemistry, for example, to look inside our bodies. And these use giant superconducting magnets to create large magnetic field. And the most sensitive magnetic sensors in the world, called superconducting quantum interference devices, whose core components are a loop of superconducting wire which contain an insulating gap called a Josephson junction. New technologies are being built and improved in the world of quantum information. Quantum cryptography takes advantage of entanglement to make communication which is extremely secure and forms the basis of the quantum internet. And quantum teleportation is the ability to perfectly copy the quantum state of an object from one location to another. Quantum bits, or qubits, are the building blocks of quantum computers, which use superposition and entanglement to create states that are practically impossible to simulate on a classical computer. The challenge is to engineer large groups of qubits that can stay coherent for long enough to perform their computations, which is not an easy task. But the potential is huge because their combined superposition means that they can explore an exponential number of states at the same time. This puts them in a different complexity class to the classical computers we use every day. There are many exciting applications of quantum computers, but my favourite is quantum simulation, the ability to simulate a quantum system, which would be amazing for things like discovering new materials with entirely new properties, or for solving computationally expensive tasks in chemistry and biology like protein folding. Now let's move on to the fields of quantum physics research. These include condensed matter physics, quantum biology, cold atom physics, quantum chemistry, nuclear physics, particle physics, and theoretical physics. Condensed matter physics is the study of large systems of many atoms in solid or liquid form, and seeking to understand their collective behaviour on a quantum level. I've placed this here because condensed matter physics covers a lot of these other fields, and condensed matter theory describes the quantum behaviour of collections of electrons in solids, which explains collective behaviours like superconductivity and the energy bands of semiconductors. There are many unsolved problems in condensed matter physics. For example, we still don't have a theoretical model that explains how high temperature superconductivity works. In a way, the frontier of condensed matter physics deals with complexity. Because the subject studies complex combinations of many atoms, which make many different materials with different physical and electronic properties, the potential avenues for study are basically endless because the combinations are endless. Quantum biology studies the role that quantum mechanics has in biological systems. There are many processes in biology that are difficult to explain without quantum mechanics being invoked, like the efficiency of energy transport and photosynthesis, to magnetoreception in birds, how our sense of smell and sight work, and how enzymes speed up chemical reactions. Cold atom physics evolved from condensed matter physics and studies gases which are controlled in magnetic or optical traps and cooled to ultra-low temperatures using laser cooling and other cooling techniques. Cold atom physics studies many exotic phases of matter like Bose-Einstein condensates and Rydberg matter, and looks at their behaviour like quantum phase transitions, quantum spin systems, and many more. Cold atom experiments can also be used as quantum simulators and also quantum sensors like gravity sensors. Because quantum mechanics describes the behaviour of electrons in atoms, it also describes the basic rules of chemistry. The Schrödinger equation is used to describe electronic structure of atoms and how molecules are bonded and move, called molecular dynamics. Solving the quantum mechanics of molecules is a very computationally intensive task, and so computational techniques are very important to quantum chemistry. A popular approach is a method called quantum Monte Carlo. Nuclear physics is the study of the nucleus of the atom and the ways that nuclei can join in nuclear fusion or split apart in nuclear fission, and also describes the particles and energy involved in these nuclear reactions. Applications of nuclear physics include nuclear power, nuclear weapons, nuclear medicine, and techniques such as MRI, ion implantation, and radiocarbon dating. Particle physics evolved from nuclear physics and is focused on understanding what the fundamental particles of the universe are and how they interact. Experiments in particle physics are performed in large particle accelerators, where high-energy particles are smashed together to make new particles out of the collision energy. This is why this field is also known as high-energy physics. The standard model of particle physics describes all of the fundamental particles we know of, which we've discovered over many decades, the last of which was the Higgs boson. A useful tool for visualizing particle interactions are Feynman diagrams, which show what happens when particles collide, and they simplify the equations of quantum field theory into much simpler pictures. The theories of the standard model include quantum electrodynamics, which describes the electromagnetic force, electroweak interactions, which includes the weak force, and quantum chromodynamics, which also describes the strong force. In the standard model, these are all quantum field theories, where particles are understood to be excitations of quantum fields, which also govern how the particles interact with each other. There may well be other particles out there that we haven't discovered yet. People have proposed that dark matter might be made of particles called weakly interacting massive particles, and the large discrepancy between the weak force and gravity, known as the hierarchy problem, may be solved by other particles called supersymmetric particles. So the frontier of particle physics is to try and work out new ways to explore the landscape of potential particles at very high energies. Now on to the field of quantum theory, which, although I've put it in this box, it really covers the whole map and has specific implementations in each of the fields. But here are some specific aspects of quantum theory worth knowing about. The core of quantum physics are the postulates of quantum mechanics that set the ground rules. The path integral formulation of quantum mechanics is a very elegant way of calculating the motion of particles by integrating over every possible path that the particle can take. And Hilbert spaces are a useful tool to describe all of the possible states of a quantum system in a giant multi-dimensional space. The symmetries of quantum mechanics are an important part of the theory to tell us the conservation rules, which are basically the rules of particle interactions. What should come out of a particle interaction based on what goes in. This is where we hit the limits of our current knowledge of quantum physics. But there are two main areas of theoretical work looking beyond the existing models. Firstly, the interpretations of quantum mechanics are attempts to resolve the counterintuitive implications of the wave function. And quantum gravity aims to reconcile quantum field theory with general relativity to make a grand theory of everything. The core of the interpretations of quantum mechanics is the measurement problem. When we make a measurement on a quantum object, its wave function suddenly changes when we detect the particle. And the laws of quantum mechanics don't contain any explanation of what is actually happening to the wave function at the instant of measurement. We also don't know if the wave function is actually real or not. And these conceptual problems in quantum mechanics are what the interpretations of quantum mechanics attempt to explain. For many years, the default approach was the Copenhagen interpretation, but other popular interpretations include pilot wave theory, the many worlds interpretation, and quantum Bayesianism, as well as many others. There's too much to get into all of them, but I've made another video which covers this ground. They're called interpretations because we don't yet have any experiments to tell which ones are real and which ones aren't. So really they're a collection of interesting ideas rather than proper physical theories. Quantum field theory is the most comprehensive description of reality we have, combining quantum mechanics with special relativity. But we know it's not a complete description as it doesn't include general relativity and gravity. There are many attempts to merge quantum mechanics and general relativity into a grand unified theory of everything, and the two main candidates are string theory and loop quantum gravity. String theory is also known as M theory, which is a theory that unites all the different consistent versions of string theory. It's very difficult to test the theories of quantum gravity because you need to go to such high energies. You'd need to build a particle accelerator like the Large Hadron Collider, but the diameter of the solar system with detectors the size of Jupiter. So currently the best hope we have of signatures of quantum gravity are from observing high energy processes in the universe, signatures from the Big Bang or black holes which might give us some clues, and this is an active area of research. So that's it, that's all of quantum physics. Congratulations, you've got to the end. Obviously, this is a lot to take in, so don't worry if you didn't get it all at the first pass, but you can always watch it again or grab this image for a reference in the future. This part of the video was sponsored by Brilliant, and if this video has made you want to learn more about quantum physics or get better at maths and science in general, Brilliant is a fantastic resource. It's a website with many courses where you can learn and solve problems at your own pace. And they've got a whole section dedicated to quantum physics, and actively learning by solving problems means that you can learn the material a lot more thoroughly than just watching videos, because nothing challenges your understanding than a good question, as I have found many times. So this is a simple, fun way to keep learning more. If that sounds interesting, go to brilliant.org/DOS or click on the link in the description below, which helps me out because they know that you've come from here. And the first 200 people to do so will get a 20% discount off the annual subscription, which unlocks all of their premium content. Also, as I mentioned at the beginning of this video, I'm selling this map as a poster, which you can find on my DFTBA store. And if you'd like to support my work, I've got a Patreon page as well. In any case, I'll be here making more videos aiming to make science easier to understand. So thanks again for watching, and I'll see you soon.